talking about
Volunteers work.
volunteers work and so on.
Okay, thank you very much for giving me an opportunity to talk about something which I know nothing about. Uh, so, so this is a work by Verlinde. Okay, so the title. Well, I wrote it that way because a lot of places they have subscript and superscript. So the paper is 12/11 6931. They have followed some notation, and I have kind of taken some liberty to change that notation, which is supposed to be a wrong thing to do in this particular field, because number of papers is equal to number of notations there. So I am increasing that by 1 by not writing a paper also. So I will try to kind of just list the notation. In case you want exactly what Verlinde are trying to say, I could write that down also. So notation is as follows. Okay, so maybe the title is black hole evaporation. And quantum error correction. Okay, so this of course involves, as you can easily figure out from the title, quantum error correction. And in case you don't know what it is, I will try to explain this thing. In case you don't know, then I'm at least in this subject I'm senior by at least few hours. Okay, just a few hours ago I have understood something which if the error correction code doesn't correct it, is supposed to be correct. So here's the notation. So I use Ij kind of state for describing black hole interior. The states of the type Nm with various subscripts attached to it are radiation. So they represent the radiation. So it may have subscript A and B or some such thing sitting around. Okay. And then there are some third notation about subscripts. And there are times when I run out of place to write subscripts, so then they become superscripts also. So they are also superscripts. And so M stands for black hole of mass M. M minus E for M minus E, black hole of mass M minus E. Re is early radiation. These are subscripts. M minus E. Okay. So it is of black hole of mass M minus E.
M minus E?
Yeah.
M was the original mass, E went out in radiation.
That is right. That's right. So one wants to write down another Hilbert space for that. Okay. And so RL is of course late radiation. And R tilde is what is called ancillary space. Okay. And I use subscript in for interior of the black hole. Maybe it's not the right thing to do. People use some tilde variables and so on, but this is what I have done.
The subscripts of
on states, on Hilbert spaces and so on. So for example, I write down a Hilbert space HM corresponding to a black hole microstates describing black hole of mass M. Okay. And our picture is something like this. Okay. And we have a stretched horizon. Most of it is not of great importance, but it is always nice to draw something like this. So states I sit here, RLs are here, REs are also there, and R tilde is here. Okay. Fine. Verlinde notation is little different. If you want, I could write that also down.
Sorry, you might have said this. In the collapse case, you won't have exactly this situation, but
yeah, we'll be looking
so there is some construction of an ancillary space in that case,
that
is it?
Right. Yeah. Yeah. So they don't really look at the collapse case.
Oh, they don't look at it.
Yeah, they don't really look at it. Ancillary spaces for this only. Okay. Sorry?
I mean, the whole issue is for a collapse case, right?
That is right. Yeah.
Information loss issue is.
Yeah, but I think they are trying to kind of give a setup in this picture, and they say that like if you talk about infalling matter, it should be possible to give a setup of that with whatever they would do with eternal geometry. Okay. So you will see that like they would actually enlarge the space in which black hole Hilbert's and black hole can radiate and go from one particular Hilbert space to another. Okay.
So this Aquila, the radiation, what exactly is Aquila?
Is the ancillary space. There is some additional space that they attach to the whole thing. Okay. So this is notation. So I have a certain amount of freedom to write whatever. Okay. If it is inconsistent, then we can take questions on that. Okay. So I will define whatever those things are. Okay. So what one does is that if you have a black hole of mass m, as I just said, we associate Hilbert space Hm to that. Okay. And you say that there exist states I belonging to this Hm. Okay. And these states I are, if you look at it kind of in a coarse grained or in a macroscopic fashion, are indistinguishable. Okay. But the microscopic description, of course, is different. You can distinguish these states, but then all that information is hidden behind the horizon. Okay. So macroscopic information is not accessible for observers sitting outside the stretched horizon. Okay. So the number of microstates which we write as n is basically given by e to the s black hole. Okay, and s black hole in this case is just the 4 pi m square. Okay. Now the assumption here that they state explicitly is that that black hole evaporation is basically treated as time evolution of all these microstates. Okay. Okay. Fine. The other assumption that they make is that right from the beginning, they assume that there is no issue with quantum mechanics, but they are not assuming that there is no drama at the horizon. Okay, so they are open about that particular point. In case something unusual happens at the horizon, they will just say that like, okay, here is the problem. Okay, if nothing happens, then they will say the horizon is smooth. Okay, so that is the place where they are not committed themselves. Okay, so they will try to maintain, whatever they will do, they will try to maintain unitarity in their setup. Okay, so suppose you look at this state and you wait for some time, then it is going to emit quantum, and suppose that quantum is of energy E, then you go to a state carrying energy m minus E. Okay. So what is happening is, so this is the mass of the black hole. So one is looking at a setup where you go from Hm to Hm minus E, where E is the energy that has been emitted in the radiation. Okay. Now clearly, if initially the black hole was in a pure state, suppose you started off like that the black hole of mass m is in precisely this state, then here it would be in a product state. Product state of state belonging to Hm minus E times the state belonging to the radiation Hilbert space. So there is a radiation space which is denoted as HR in general. Okay. So right now, okay. So the state that one gets here is basically belongs to Hm minus E tensor HR. Yeah. Is there a question? Okay.
Are you going to tell us how to pin the chain on the
No. Yeah. Okay, so the idea is to actually enlarge the space instead of looking at it in this fashion. One is trying to kind of enlarge the space. So write down total Hilbert space H to be tensor product of H black hole times H radiation. Okay. And this H black hole state itself is a direct sum of
the black hole has gone from Hm to Hm minus E cross HR, right?
yeah.
It's not Hm to Hm minus E. It's Hm minus E to Hm minus E cross HR.
That is right. So I just said that Hm goes to Hm minus C for the black hole. Then there is a radiation. So the total space that you have in which this new product state belongs to is Hm minus E tensor HR.
I see.
So the time evolution operator actually takes Hm to.
Yeah. So time evolution operator does this.
Yeah. Right.
Okay. But if you look at only black hole, then you go from Hm to Hm minus E. Okay. You look at only the black hole and forget about the radiation. Okay. So this is just for setting it up to write down something that in which you write down H black hole to be a direct sum of all these Hilbert spaces. Okay. So you write down a larger Hilbert space in which you write down H black hole tensor H radiation. Okay, and H black hole is a direct sum of this. So the purpose of doing this is that not only that you know start with the initial state, but you are trying to track the trajectory of the black hole as it evaporates. So you add different Hilbert spaces, and then in a bigger Hilbert space you try to follow the trajectory as to how the black hole plus radiation is going to I mean the path that it is going to follow.
Similar thing for HR as well? Again. I mean, to
is,
begin with, presumably the HR was empty and then slowly HR fills up.
That is right. But one is trying to look at HR as radiation Hilbert space in outside. So I can just write down a free scalar field in the
And include all states.
and include all the states. Okay. So its occupation number would change, but the Hilbert space by itself wouldn't change. Okay, but never.
I did not follow the notation. So
Yeah.
sorry. HME I understood. What do you do with HBH or?
Yeah. So what? So that is the reason why I wrote it in this weird ordered actually. Okay. So the thing is the following: that you start with a black hole of mass m, you assign a Hilbert space to that. Okay. That contains this number of states of this kind. So that many kind of states are there in HM. Okay. Now, if that black hole radiates a quantum of energy E, say, then it has become a black hole of mass m minus e. So what you do is that you say that that new black hole belongs to the Hilbert space Hm minus e. Okay, just looking at the black hole right now. Okay, now of course the quantum that you have emitted goes outside. So there is the radiation Hilbert space sitting outside. It kind of occupies some state there. Okay, so if you look at the total Hilbert space, you started from Hm and you went to Hm minus e tensor Hr. Okay, some state has been occupied in that tensor product state. Okay, now you can imagine next step, that is another quantum has been emitted by a black hole, and it may go to Hm minus E1, say. Okay, where E1 is the energy of the new quantum. So that corresponds to another Hilbert space. Okay, so you are going to kind of keep going from one Hilbert space to another Hilbert space. Instead of doing that, what one does is that writes down much bigger Hilbert space, which contains H, where you define H black hole to be a Hilbert space which is a direct sum of all these Hilbert spaces. Okay, very, very highly redundant. Yeah. Okay. So in fact, like once you make one shift, then the previous Hilbert space has essentially become useless. Okay. But yes, that is the kind of description one is trying to give. Okay. But that is right. At any given time, only one member of this times the H radiation is really in the game.
Only one element of HME is in the game.
Yeah, only one element of HB in this sum, tensored with HR, is in the game.
Correct.
Then next instant somebody else and HR is in the game. Okay, so in that sense it is highly redundant. There is large part of the Hilbert space which is sitting there doing nothing really.
Okay. So HR you also construct like this, right?
No. HR is radiation in the region outside the spectral horizon. I think of that as kind of moderately curved space. Write down radiation field, whether it is free field in the curved space or maybe even interacting field, and just do mode expansion and write down corresponding states. Okay. So for that, in fact, I could just work with free fields and just write down A dagger A or B dagger B, whatever. I'll do that. Okay. So, but I define it once and for all. Okay. Now, more and more quanta are emitted, they just change the occupation number in that Hilbert space. Okay. Whereas black hole Hilbert space, you actually go from one subsector to another subsector. Okay.
Suppose you just take the point of view that there is some density of states inside, and interpret this direct sum as an integral over energy of different Hilbert spaces corresponding to microcanonical ensembles. No?
Okay.
Maybe that's what is meant, like you build up all the states up to a certain n.
Okay.
And that is the HBH.
No, but she is not
making
a sum over, are you taking a sum over energy shells? Or is it like at any point it's all the way up to, it's cumulative?
At any point it is all the way up to that energy.
Yeah, it's cumulative. So it is redundant because of that.
You know, that like you have some black hole up to some energy, say m, then all states are included. Then you go from m to m minus e, then all these states are included in a new Hilbert space. So in that sense, there is a redundant description. Because whatever was in m, most of it is there in m minus e also. Okay.
But it's not redundant in the sense that
if you start from a black hole of mass m, right?
Yeah.
There is a small probability that even after the lifetime of the black hole, it will remain at mass m, right? So if you are trying to construct the full wave function of the state, you also have a small probability that it's in the state m with no radiation.
Yeah.
Right?
Yeah. That is also true.
So the time evolution will be a linear combination of all of these.
Yes.
States.
Yes. Yeah. Also, I mean, like in some sense, if the black hole emits certain radiation, then the problem of determining the spectrum has to be redone. So in that sense also it is not completely redundant, in the sense that same set of states have been pushed, except one is not what is being done actually. So let's put it this way, that take any element here of any mass, say m prime, okay, which could be m minus e, m minus e1, minus e2 or whatever. So let's call it m prime. Every such element here is a Hilbert space corresponding to an eternal black hole. Okay, and it is a direct sum of all those eternal black hole Hilbert spaces. Okay, and they may have actually different spectra.
Every term here is a Hilbert space of eternal black hole.
In a way, yes.
How
Yeah.
does that follow? I mean,
No, it is just to think of it in that particular fashion. That you just take a black hole as a stationary object.
You don't mean something like two-sided thing, but just that it's a stationary.
Take a stationary thing, solve the eigenvalue problem, and write down the Hilbert space. In that sense, that yeah. Don't assume that it is emitting anything or something. Just take it as a stationary object, solve the problem, write down the Hilbert space. Then take another fellow, solve the problem, write down the Hilbert space. In that sense.
In DSCFT, you just have so many states at this energy.
Yes. Yes. Yes.
Thank you.
So the dimension of HR is same as the dimension of M?
No.
But suppose the case, I'm not changing HR, right?
Yeah.
So-
HR is infinite dimensional.
HR is, I mean, suppose everything evaporates, then HR would be, say, totally.
See, HR is infinite dimensional, first of all. And second thing is that, like, if you are looking at bosonic field corresponding to this radiation, its occupation number can be arbitrary. Okay. So even if it was finite dimensional, there is no issue about that. But anyway, we are looking at radiation in the space outside the horizon. Okay, that is kind of infinite space in which you have, I mean, you essentially have a continuous spectrum. Okay. Fine. Yeah. So as I said, that this HR is a radiation Hilbert space which belongs to the Rindler wedge. Sir, it's called right range. Okay, right in the sense of not being correct but right. Yeah.
This is not really, this is something that works at infinite n. It's direct product structure.
Infinite what?
At infinite n, when no interactions are present. It's not really true that the state is black hole and radiation are not really independent when they're interacting.
That is right.
So it's not
But
really
that-
true that one can have a direct product separation of the Hilbert space in this form.
That is right. But like I will mimic that by writing down interaction Hamiltonian, which kind of makes these fellows talk to each other.
In the CFT, I think there's no nice distinction you have between, I just give you some state.
Yeah.
That state looks like it has a gas of gravitons on top of the black hole. I don't think there's any sense
Yeah.
in which,
I
except
agree.
in the infinite n, you can separate what is the black hole part of the state and what's the
That
gas.
is because it is CFT. I didn't say that I'm doing CFT.
Okay, rather let me try to give a slightly, exactly. Think of the full D3 brane geometry, okay?
Yeah.
Then the near horizon region, actually, the stretched horizon is the CFT. Okay?
Yeah.
Which is the
But
black
not
hole
far
that
away.
is up here, and the asymptotic gravitons which have reached other radiation.
Yeah.
Then you really have a tensor product.
That is right.
For some very special cases where there's some decoupling at low energies or something, right? It's not really true.
The
Yeah.
the stretched horizon is similar, no? That everything that crosses the stretched horizon is encoded in some dynamics on the stretched
Yeah.
horizon. And
So-
that is
And the ADS is different because of this reflection and you are in harmonic.
That is right. Yeah. Not for the open this thing. Not for asymptotically
I
Minkowski
mean, the
case.
decoupling is sharper, but I'm saying the fact that you could have a tensor product Hilbert space could be more sharp.
Yeah. So in the vicinity of stretched horizon, one will try to introduce a kind of local interaction term where these two Hilbert spaces will talk to each other. Okay, but that is it. I mean, once it has gone outside the range of stretched horizon, then you essentially treat them as free. Okay. In fact,
Hamiltonian is not block diagonal in this case. The Hamiltonian.
yeah, Hamiltonian is not.
Yeah.
Full Hamiltonian.
Yeah, full Hamiltonian will talk, connect that.
Yes. So the Hamiltonian will be a H black hole, H radiation, and H interaction. But that H interaction will be treated as some local interaction Hamiltonian, where this interaction takes place in the vicinity of stressed horizon. But once the radiation gets out sufficiently far from the stressed horizon, then you essentially treat that as kind of freely propagating objects. Okay, they are not even going to be part of the game, in fact. Okay, at least early radiation. So right now we have just written down HR. We are going to decompose this also into early and late radiation. But so let's first at least get this. Okay. And the aim is to show that Hawking radiation is a unitary process. In this big Hilbert space H. Okay. Capital H is the full Hilbert space.
HBH cross H, yeah, I see.
This is a full Hilbert space. Okay. So this is the direct sum of all these eternal black hole states tensored with the radiation. And when I say unitary process, I mean that one is thinking of a Hamiltonian evolution of the system in this Hilbert space, which is unitary. Okay, that is what one wants to kind of do. Okay, is it fine? Okay, so here are a couple of examples. What are called young black hole. Okay, and the old black hole. So let's start with young black hole. So young black hole of mass m is basically interpreted as state I belonging to a HM, of course. Okay, and you basically say that this young black hole is in pure state. Okay, so this is okay. But it would start radiating at some point, and you can ask after some time t or tau, whatever, what happens to this particular black hole. Okay, so even if black hole is in this particular state, you could still say that with respect to the full Hilbert space, which is this, you can say that black hole is something like I tensored with some phi I, which is some surrounding. Okay, but they are pure states. So therefore, if you want to write on a density matrix corresponding to that, you can just trace over phi I. Okay, and that will give you a pure density matrix rho, which is like that. Okay, because they are not entangled states at all. Okay. So what if we look at old black hole? Again, mass is m. So what do you mean by surrounding? Surrounding means like that there is a black hole, and then there is a space which is sitting outside, which could have all kinds of material. Okay. Outside the horizon, yeah. So this Hilbert space is basically describing only black hole interior. Okay. Outside you could have something which doesn't talk to the black hole. Okay, it is not correlated with it. It can, so you may want to write down this as a state corresponding to the full Hilbert space H. But since they are not talking to each other, you could just integrate it out and you still get a pure density matrix. Okay, that is the point. Now, what is the distinction between old black hole and young black hole? Old black hole is the one which was young at some point. Well, it has been radiating for quite some time. So the state that one wants to write down here is something like this. Is something like 1 over square root n summation I okay. where phi I denotes early radiation. Okay, so let me kind of step back a little. When I say young black hole of mass m, when I am doing this check, I claim that I am doing this check at time t is equal to 0. Okay, the black hole is just formed. Okay, and this is a statement about it. Old black hole, check is again at t is equal to 0, but it was formed long ago. Okay, it was formed at t equals very large negative value, and it has been radiating. Okay, and here is the entangled state where phi I corresponds to early radiation and I corresponds to some of the black hole microstates. Okay. Now the thing is that, like, since the black hole has been radiating for quite some time, the number of states here are much larger. Phi I are much larger than say I. Okay. So in other words, the black hole microstates are entangled with the states outside, but since phi i's are much larger in number, you could say that that these phi i's can be written in terms of orthogonal basis. Okay, so you can orthonormalize them. Good. So this is, sorry?
When all the phi i's don't appear.
All the phi i's?
If you
Yes.
make a change, the number of
Yes.
phi i's is only equal to number of
Yes,
phi i's.
not all the phi i's, so it would appear. Okay, because it is highly maximally entangled thing. Okay, and so this corresponds to the statement that I just said.
Also, if they're orthonormal, you might want some coefficients, no? If I and
Yes.
phi are both orthonormal.
Yes. If you are saying they are maximally entangled, then the number is basically 1.
Well, okay, but in a
density matrix to be just I, right?
in a
Yeah.
density matrix. But for real case, black hole case, there will be some e to the minus beta ei kind of coefficients.
That is right. But like,
Maximal entanglement is not a fair.
yeah.
Whether he is writing it in the canonical ensemble or in the microcanonical.
Yeah, that's right. If I sum over, trace over one of them, then I will get a beta e sitting around. Okay. So
in phi I, what is I takes?
it is just saying that, like, this state is entangled with this state. Okay, there is a one-to-one.
But the same phi I can be entangled with anything.
No, it is maximally entangled.
With only one.
Yeah. Okay, so number of phi i's could be large in number, but like given that the number of states in the black hole is depleted, the maximal entanglement tells you that there is one-to-one map between them. Okay, so what I was saying here was early radiations, Hilbert space is much bigger than okay. So what we could do is that we could trace over the early radiation. So this is okay, and write down the density matrix corresponding to the black hole. Okay. So if you do that, then because of maximal entanglement, you get H old black hole. This can be written as 1 over n summation. Okay. So this basically corresponds to some identity matrix corresponding to the black hole of mass A. Okay. So this m doesn't mean the dimension of that is m, but the dimension of that is e to the 4 pi m squared actually. Okay. Fine. Yes.
These states I which correspond to the black hole,
Yeah.
they are not lying in any particular script h m minus e, right? Because in general they can be a spread. I mean, there's a quantum mechanical probability of some amount of energy
That's
having
right.
come out in radiation and
Yeah.
some other. That
Yeah,
is
there is
tied to
certain
the
amount of
question.
uncertainty which one has to. Yeah. So this factoring does not does not necessarily does not mean that like black hole belongs to only one of them at any given time.
But then is
there
the
is of course a
density
spread.
matrix really proportional to identity in this sense? That is to say, there's some, just to understand, you wait till some time t. Now there is a probability that some amount of energy came out in radiation, or a little less, etc., with some spread. Now, if some amount of energy had come out, then the remaining energy in the black hole is probably evenly divided among all states. But
I understand. So like suppose I look at this state and I say that like, okay, this is maximally entangled, suppose. Then a few minutes later, say, there is the emission of a quantum, and then I want to ask the same question, is it maximally entangled? Okay, which is related to the thing that you are trying to say. And I want to say that the firewall statement is the assumption, okay, that's what I am going to say, is the assumption that it is maximally entangled at time t is equal to 0, and it is essentially maximally entangled at time t is equal to tau, okay, when some quantum has already been emitted. Okay. So it is related to your statement that both of them cannot be simultaneously really true. But if you assume both of them to be simultaneously true, then you will encounter this firewall problem. Okay, so clearly that means that even at this point I shouldn't be making the statement that it has to be maximally entangled.
That's exactly right.
But if you grant me this, that at time t equals 0 it is maximally entangled, then at time t is equal to tau, I cannot again say that it is maximally entangled. Okay, so therefore you could have reversed the argument and said that even at t equals 0 you couldn't have done it really. Okay, but let's take it kind of that kind of approach right now and see the contradiction.
So just one question: this maximal entanglement we don't really require. Right? There's this other concept as we were discussing yesterday, this Smith index, which tells you whether all the states really appear in the entanglement or not.
Yeah.
That's what we really want. No, we don't want it to be literally the identity. If it's something else, that's okay as long as there are no zero eigenvalues.
Yeah, that is right.
And that will be true after the time.
Right, that's what I'm saying. That you really take this kind of sharp statement of this kind, okay, which shouldn't be true at any instant.
If you added some coefficients, it would be true at all times, right? If I just added some sum of I, di, I, then this statement would be true at all times.
That is right.
And somehow the identity is actually important, that it's the identity and not something else.
To put the firewall statement in the highest contrast, it is useful to state it this way. Okay.
Yeah, because then the body, if it's not maximally entangled, then if you emit another quanta, right?
Yeah.
You want to show that B and C are maximally entangled.
You don't need to have it be maximally entangled.
Okay, but there's some entanglement.
Yes, as long as there's some, it's okay. So if you have DIs there, I don't think that creates any.
Yeah, but it still has to be large entanglement. I think that is why, because it has to kind of have this conflict with subadditivity also.
I think the Hawking partner and across the horizon should be maximally entangled almost for it to be anything like the Minkowski vacuum. And to the extent they are maximally entangled, you can't entertain any entanglement here, probably.
If I put a DI here, I think that's okay. It doesn't spoil this paradox. So
yeah, I agree.
There without losing the identity.
I was just saying it because the Hawking partners have to be more or less maximally entangled, and then monogamous nature means you can't be entangled with this stuff.
Yeah.
You don't have to be maximally entangled, you just can't.
That is right. That is right. Yeah.
Wait. So, this monogamous thing does not require maximally for one set? It's just entanglement.
What you can show is that if A and B are maximally entangled, then B can't be entangled with C. That's enough.
Correct. But so the...
You don't require B to be maximally entangled with C to get a complete.
But you want to state it in terms of this Smith number. A has maximal Smith. All states in A are entangled with something in B. Then by I can generate any operator acting on A by an operator acting on B. Even if I had some coefficients di, then I can always tell you the result of any experiment I perform in the first Hilbert space by an equivalent experiment in the second Hilbert space. That's the only thing you really want. You don't want it to be identity. As long as I can tell the result of the first, in any experiment in the first Hilbert space by some other experiment in the second Hilbert space, that's all you really need, I think. The information has to be there about the first Hilbert space and the second Hilbert space. If I put coefficients, I don't think that...
So even if the Hawking pairs are not entangled with coefficient 1, the paradox, this monogamous thing would still be true because the outside, the late and the early will, is that or what?
Something has to be nearly,
No,
A, B and C can have some degree of entanglement with each other. It's only if you try to maximally and nearly maximally entangle A and B that then there's a problem having some entanglement with C.
But suppose I say that the particular Hawking quantum which is being emitted, right, that coefficient is very, very small. Then how?
If the particular, so here SBC have to be maximally entangled, close to being, that's
Yeah.
up to 1 dimension.
Yes. So suppose the corresponding B is entangled with the early radiation by a very small coefficient.
Then it's okay. Then you won't have a contradiction. You're right. So you want the coefficient not to be very small, but generically, if I introduce some DI things here, that coefficient I'll get will not be very small. It will be, you know, the way you'll get a very small coefficient is by having one of the D1 say very large and everything else being very small.
Very
It's
small.
almost like a pure density.
I mean, that will happen in the extreme case. If you have an extreme black hole, you will actually have that situation when it's disentangled.
Is one of them is very large and the rest all are extremely small.
If you take an extremal black hole, that's what will happen.
Yes.
Because there's no radiation, you're saying.
Yeah, I mean, in the sense that
but it's also a pure state in some sense.
It's a pure.
Yes.
Yeah.
That's right.
That's
But I'm just saying that by adding some coefficients DI and not having IM, but having, as long as all the entries are roughly non-zero, I think you're okay. As long as the phenomenon entropy is not very close to zero, you're okay.
I mean, those coefficients have to eventually make for a fully unitary state in all of them.
Yeah, I agree. I mean, this state doesn't have to be maximally entangled. I agree. I'm trying to use it right now to just kind of state the firewall contradiction. Okay. Fine. So let's look at the firewall statement. So the firewall statement is the following, that let us decompose the Hilbert space H into late Hilbert space tensored with early Hilbert space. Okay, so this is okay. So early Hilbert space is of course the radiation. Late Hilbert space will of course contain the black hole. Okay, so we'll write down the late Hilbert space to be something like. So this is a place where I kind of choose a notation to call Hn corresponding to black hole states, Hilbert space corresponding to the inside of the black hole, times H late radiation. Okay. Yeah. Okay. So now the thing that one says in the firewall argument is basically that we have a density matrix rho late, which you can derive from this, from whatever we have started off with, would be a mixed state. If, yes, I'll tell you. So if T is equal to set tau. Okay, old black hole is something which has been, which was formed long ago and has been radiating, and I define it to be an old black hole at time T is equal to 0. So it was formed long ago and has been radiating for some time.
So actually T equal to 0 is already past the page time.
Yes, T is equal to 0 for this black hole is all way past the page time. Okay, at that time I have large amount of early radiation which have already kind of gone out of the near staged horizon region. States in, so here is the first subscript B. So this is a radiation state. So you can write down equation for the radiation field, expand it in Fourier modes, and then you have B and B dagger as creation annihilation creation operators, and then N is corresponding occupation number. Yes.
So just one, so in HR, suppose I am before T is equal to 0. So suppose two quanta come in, one with another. Will I think of them as HR1 cross HR2 or just HR?
No, they are still in HR. It is just a multi-particle state that you are looking at in HR.
But now here after T is equal to 0, I am thinking of HR, new HR to be HRE times HRL.
No, what I am going to do is I am going to forget about this HRE by writing down density matrix and then just look at this part of the story.
So I guess this question is, why is it a direct product and not a direct sum? That Hilbert space derivative.
Which one?
The H.
This was always direct product.
That's what you were asking.
No, I'm asking, so HR, suppose that before t is equal to 0, also quantas were coming out.
Yeah.
We are treating it as a single HR, right?
Yeah.
Not cross product.
That is right.
But after t is equal to 0, whatever mode is coming out,
Yeah.
I'm treating as HRE cross H R1, say.
Yes.
Why is it?
So I just kind of traced over the early radiation, and now I look at only black hole and a new radiation coming out of the black hole, and I want to trace that. Pictorially, what has happened is that like the old black hole has radiated for a long time. Okay, at time t equals 0, I find that large amount of radiation has gone out way beyond the near stretched horizon region. Okay, so anything which has gone out, I basically forget about it. They are kind of free streaming radiation, and I just sum over that stuff and look at this object as a new object written in terms of density matrix, because there was certain amount of entanglement of the black hole with the radiation which is free streaming now. Okay, write down a new mixed state, okay, or the density matrix corresponding to that. Okay, and then ask what happens when the new radiation comes out. Okay, so in other words, this entanglement information between the early radiation and the black hole at time t is equal to 0, okay, has been summed up into writing that density matrix. Okay, and then you look at what happens. So I could have forgotten about writing E and L here, because eventually I am not going to kind of play with this object at all. Most of the game is here. Okay, so this state NB is something like 1 over, say, square root of something like product over omega n omega factorial times b omega dagger to the n.
Radiation is within the stretched horizon, or it's come out in this picture?
Late radiation is no, it is outside the stretched horizon.
Outside the stretched.
Yeah, it is outside the stretched horizon, but it has not gone. Yeah, it has not gone far away. Okay, whatever is called early radiation has gone sufficiently far that you could kind of forget about it. But late radiation is outside the stretched horizon. Okay. Okay. Fine. So now we can define rho late to be something where where we basically sum over n and m, rho and m, okay, where rho and m is basically the reduced density matrix. Okay. So what if we trace over the internal degrees of freedom of the black hole for when we are looking at rho late? Then you can write down rho late radiation, and rho late radiation is basically trace over internal degrees of freedom of rho late. Okay, and that quantity can be written down as where Wn is basically e to the minus beta En upon, say, Z, where Z is a sum over n. Okay. Beta is of course the temperature. Okay. So now remember that like we are looking at a state where the black hole really has mass m minus e or m minus En maybe. Okay. So at t is equal to tau, mass is m minus e, and radiation has energy En. So therefore the dimension of the Hilbert space of mass m minus En is basically, I I write that as Nn is n times e to the minus beta En. Okay. And if you take this formula and plug it up there, okay, then you find that the dimension of the black hole Hilbert space is going to be n times z, because there is going to be sum over n e to the minus beta En. Okay. Okay. So now the AMP's argument. So AMP's argue that that if you started off with the density matrix of this kind, okay, and if you radiate one quantum, okay, then you get a density matrix corresponding to a black hole of this type, which doesn't really change very much. Okay. So their claim is rho nm. So let me call it AMPs. So their claim is this is going to look like 1 over nz times delta nm times identity of m minus em. Okay. So this is really kind of putting it in maximally with maximum contrast. Okay. So now if you do this, then you can ask what is the mutual information. So mutual information is, so I use subscript and superscript here, the internal degrees of freedom and the late radiation is defined as black hole entropy plus the radiation entropy minus the relative entropy. Yes. What is the question? Okay. So we can compute within the AMP's picture, which is basically starting from this point onwards, taking everything to be maximally entangled. The black hole entropy is going to be log of nz. Sorry, black hole entropy is not that. Black hole entropy is log of n minus beta En. Okay. So I could kind of, I don't even have to take En, I could just take some average energy. Okay. Then the radiation entropy is going to be log of z plus beta E bar. Sorry. Yeah, Sn is the black hole which is defined at time t plus tau, sorry, at time t is equal to tau. Yeah, n is just the internal degrees of freedom of the black hole. Okay. So I could have continued kind of calling it, so they have used words A's and B's and so on. Okay, but there are places where they have kind of conjugated it, and then there are capital A's and small a's also, and so on. So I try to kind of avoid that. But in case you don't want that, I could just say that this is the SA, where A is the part which is across the horizon. B is the one where there are these B radiation modes. Okay, so capital A. Okay, so if you want to use Verlinden notation is capital A. Okay, and then from this you can find out what is S in or capital A and late radiation, and that quantity is log of nz. Okay, so you can just plug this in now. So if you plug this in, you get I late radiation with the inside of the black hole. Just plug in these numbers, the answer is 0. Okay. So what this says is that the late radiation has no mutual information with the black hole. Okay. On the other hand, the Hawking pair, which is created at the horizon, you know that at the horizon there is certainly entanglement. Okay, you can compute when you look at Hawking pair creation that that this implies basically that there exists entanglement at horizon. Okay. So this is a contradiction basically. This is what they say, that like you know that there is, if you take the horizon to be smooth, you can find out what is the entanglement across the horizon. Okay. On the other hand, mutual information is really 0. Okay. And so therefore, if you say that such a thing happens, then there has to be some way that this information, I mean there has to be something which blocks this information to go across. In other words, this second statement that there is an entanglement across the horizon is not correct. Okay. So they conclude basically that there exists no smooth horizon. Yes.
This is mutual information between the late radiation.
Late radiation and the black hole. Okay. Sorry? Oh, the flaw is in the, I mean, there can be several flaws, but one of them is that like if you grant that this is maximally entangled, okay, then after the radiation you cannot say that the next state is again mostly like this. Okay. So then at every evaporation stage you continue to be in maximally entangled state with respect to the radiation, which is not correct. Okay. So what one could do is to kind of relax this condition and see what it does. Okay. Okay, so let us try to understand what has happened here. Okay, so first thing that you find that in the Am's argument, the mutual entropy is S in RL is equal to log of NZ. Okay, whereas the entropy of the black hole, okay, itself is log of Z, sorry, log of N. Okay. So this mutual, the shared information or the entropy is larger than the black hole entropy itself. Okay. So, so it looks like a contradiction, but one of the reasons why such a thing happens is simply because we have, we are like writing down a much bigger Hilbert space, okay, which is like much larger than the number of states the black hole has. And therefore, as the evaporation takes place, the black hole kind of spreads out into a much larger Hilbert space, and that is the reason why you do get larger number of states in S in RL. Okay. But then you want the evolution or time evolution to be unitary. Right? It should maintain unitarity. Okay. So that implies that whatever risk statement that one has made, okay, where one could say that like, okay, this is a, sorry, not here, that this is a coarse-grained statement, that okay, it is almost like this plus some corrections and so on. Okay. Then you would say that the microstates or S black hole, but micro, should remain same. Okay, this number shouldn't change. Okay. Okay, so only way one could do this is to say that the late this thing. So if you look at the black hole late density matrix, it doesn't have.
Same, I didn't understand.
In the sense that like you are evolving every macro state of the black hole, right? So in the big Hilbert space, in the full Hilbert space edge, okay, the number of states are not being lost, right? That is what you mean by unitary evolution, okay, right? So
you're just saying the dimension, isn't that right? You're saying, I mean, how is SBH micro being defined? Sorry.
So like I take say black hole at time say t is equal to 0. Okay. Okay, and then I look at what are the internal degrees of freedom. all
density
degrees of freedom which
matrix,
have gone
right?
out far away, I have integrated out and written down a density matrix.
Yeah.
Now, at any other time, that number has to remain constant in a full Hilbert space.
But see, this is where I'm a bit confused. Sorry. There is an abstract Hilbert space which is the sum over all H M E.
Yes.
Its dimension is of course just fixed,
Yeah.
whatever it is.
Yeah.
But if you're going to look at the state of the system at some point,
Yeah.
trace over all the radiation degrees of freedom and then define an entropy for the black hole and call that SBH micro,
Yeah.
then that number can change, right?
That number for black hole would change, but once, okay, SBH micro at t equals 0
Oh,
is defined at t equals 0. This number in a full Hilbert space remains the same. Full Hilbert space contains all direct sum of the black hole states tensored with the radiation, with late radiation. Yeah. Already, yeah, RE is already gone. Yeah.
okay. So you are including the late radiation in SBH.
Everything. So I define
then-
the black
then
hole.
I agree.
I forget about all early radiation. I define the black hole at time t equals 0, find out what is its entropy, okay, and then I say that a big Hilbert space defined H as H, which is now little different actually, which is H black hole tensored with H late radiation only.
Okay, then I
Okay.
understand.
In
So,
this thing, the
Fine.
unitary evolution means this
Fine.
number doesn't change.
Sure.
Okay. So only way out of this is to say that like this has off diagonal pieces.
And what was this?
Which have been
turning
missed out here.
I missed something. What was SPH micro turning out to be with that diagonal ansatz? As a function of time or something? It was not
Yeah.
remaining the same, right?
No, at a fixed time it is just the counting of those states. They are all micro states.
No, sorry. So this should remain the same. And
Yes. So
then-
look at this. This is the old black hole at time t equals 0. I sum over all the radiation which has gone out. Okay. So then I get density matrix corresponding to this. Okay. That has n states. N is
So log
e
n.
to the 4 pi m squared. Okay. Log of that. Yeah. Which is
So log of n.
Yeah.
And if I had assumed that at a later time, the density matrix was rho amps,
yeah.
because that is for late radiation and black hole.
That is right. Yeah. This is the one which is the kind of mutual information.
What would SBH microcomputed from there have turned out to be? Sorry, you did it, but I'm just trying to make sure. Would it have turned out to be SBH micro at t equal to 0? No, right?
no,
Or,
no.
And what would it have turned out to be? Sorry.
Yeah, so-
you've done this, but just to know.
No, I think with M's ansatz, he's saying that it will be log of nz. Right? That
Yeah. With AMS answers, this is going to be the final number, I think.
So it started off as log n,
Yeah.
and it is turning out to be log of n.
In Z. Yeah.
And z
Is
sum over all radiation.
all radiation states.
So it's the total entropy in a gas of radiation over what size? It depends on what you define by late, is it?
That is right. Yeah.
So it's
Yeah.
a
So you know, like at time t is equal to 0, you have defined this thing. Then at time t equals t, you know where is the horizon of that free streaming object. Okay. So you could define it over that volume. But the states are not even defined that way. States are defined over entire space. So it is not that they are in that radiation is in the box. The radiation is in the free space.
But there's something not quite adding up for me, because the entropy in the radiation is going up clearly,
Yeah.
but in the black hole should be at least decreasing, right?
Yeah. No, but this is the total thing.
Yeah, so the total seems to be only increasing like the log of the entropy in the radiation. is it?
Radiation, yeah.
It seems like too big an increase. Or
No, it
are
is,
we accounting for the fact that m minus e's dimension is also shrinking?
no. That also they have not taken into account.
That we
yeah.
have to do. They're not
Yeah, that
taking-
one is to
that's
take into
not
account.
okay then,
Yeah.
right?
So they have not done that also.
Oh, I see. So
Yeah.
then they'll get this.
Yes.
Otherwise, it will be less.
Yeah, so the increase is not that drastic as it looks, because they have not even corrected the mass of the black hole.
Thank you. That's what was confusing.
something is bothering me here. That 1 over nz, then whatever that, these are
Yeah.
these are different number of. So That's isn't that the same thing as psi old being 1 over square root of n I phi I or not? Is that a different?
This one? Yeah, this is at time t equals 0.
What I mean is that how many dimensional identity matrix is that there?
This one?
Yeah, it's.
This identity matrix is whatever.
You mean NZ cross NZ identity
yeah.
matrix?
No, e to the, no, there is a delta m in here, which is a radiation this thing, and this is only the black hole thing, which is e to the 4 pi m minus e square. That is the number.
Okay, we can discuss this. I'm confused about the normalization. That 1 over NZ, the trace of, how is it an NZ cross NZ unit matrix?
No, it is not NZ cross NZ.
I mean, the trace of rho and m has to be 1. We can discuss this later. I mean, right, the trace of that density matrix should be equal to 1.
You mean rho amps? Is that what you're asking?
Yeah, this rho amps isn't this the reduced? Sorry, maybe I'm getting.
Rho amps is 1 because if the identity of m minus en is still over an n-dimensional space, then that trace is n and trace of delta nm is z.
Yeah, trace of delta nm would be z, and although this is written to be m minus en, it is still taken to be n. That is why that 1 over n.
Oh.
That is z, even though z is defined with this factor of e to the minus beta en, right?
Yeah. Yeah.
But there it's just delta nm.
Yeah, that is just counting each state.
So the trace naively is not 1.
Trace, yeah, naive trace is not exactly 1. Yeah, I agree. Yeah. But okay, you are saying that one could just write down e to the minus beta?
Yeah.
Yeah, one could do that. It doesn't make much of a difference. Yeah. Yeah. Yeah, one could do that.
Yeah.
But it doesn't change this argument very much. Okay. So let's kind of consider the so let's look at the Hamiltonian for this system, and how much time do I have? 3:45. I see. Okay. So far error correction has not appeared. Yeah, error correction has not appeared. Yeah, so that's why I'm trying to kind of go quickly. Okay, so let's, sorry? Error correction, yeah, that's right. So let's look at the Hamiltonian H, which is Hamiltonian for the black hole, plus Hamiltonian for the radiation, plus interaction Hamiltonian. Okay? And we can write down, say, quantum state of radiation to be something like phi to be like this times phi I. So this belongs to the early radiation, and this is the late radiation, and we are writing this at time t equals 0. That's why we are in a vacuum state, okay, for the late radiation. And what we did earlier here was that we did not even consider this Hilbert space, and we just looked at the early radiation and just summed it over. Now we will just keep this and write down the rho corresponding to this. So rho old at t is equal to 0 is going to look like the earlier rho old that we had written down, which probably I just erased. No, it's right here. Okay, times this is a late radiation. Sorry. So this is a vacuum state of late radiation at time t equals 0. Okay, which was not taken into account earlier at all. Okay.
So say that again. Of the late radiation vacuum state at t equals 0.
At t equals 0. Yeah. Early radiation we kind of traced over, but then we got only I, and that is what it was, but now it is not I but this one also. Okay. Fine. So let's look at a pure state. Okay. So suppose you look at the state I times 0. Okay. And we want to look at the time evolution of this state. So time evolution of this state, remember we are working in a interacting system. Let's work in the interaction picture. So time evolution of this system would be done by u tau, where u tau is a unitary time evolution operator containing only interaction Hamiltonian. Okay, e to the minus I h interaction t integrated and stuff like that. Okay. Fine. So let's write down this system u tau as sum over states n and j, okay, times c I n j. Okay. So I is the so this is a pure state and it evolves into some combination of these states where n are specific excitations in the late radiations and j are black hole states. Okay. Fine. So Cnji can be written as sorry, and Cn itself is an operator which is expectation value in the of this unitary transformation from 0 to n. Okay. So what does this do? The Cn is actually a map from Hm to Hm minus e. And C dagger of course would do the reverse. Okay. And unitarity of this thing u dagger u is equal to 1 is a statement that Cnji Cnji summation over n and j is, or maybe let me put it k is equal to delta ik. Okay. So where u is this unitary time evolution operator. So these are the matrices, Cn are matrices which relate the pure state to new state as you evolve the system from time t is equal to t1 to t2 say. In this particular case 0 to tau, sorry. Okay. So one could try to write down this H interaction in some form. Okay. Although I am not going to write this thing is very speculative, but like you say that ingoing mode or the radiation times some V of some operator plus outgoing mode and some other operator. And they try to give some ADS-CFT related kind of interpretation to this as phi being the bulk radiation degrees of freedom and V being some operators on the boundary and so on. Okay, not really relevant right now. Okay, only thing is that basically these operator C's which actually relate Hm to Hm minus E should be related to these V's. That is the main point. Okay.
So you introduced earlier H black hole as sum over all the HMs, right? HM2.
Yeah, yeah.
Now what you are doing? I mean, you have only one Hilbert space, right? Which is just
That's
direct
right.
sum over.
But within that there are subspaces and these operators relate them. Okay. Fine. So let's get back to our old black hole now. So rho old now at late time can be written as u rho old at time t equals 0 u dagger. Okay. And rho old itself was 1 over n times the identity matrix tensored with 0b 0. Okay. So you can check, this is not difficult to see, that you can show that rho old nm is basically equal to 1 over n times Cn Cm star. or maybe since it's an operator, I should put dagger. Okay. So it is just being computed in the radiation state n and m, and you can show that that is a value. Okay. Fine. So one thing that one can easily see here, which we couldn't see in the earlier description, is that rho old late squared is equal to 1 over n times rho old late. So it's almost like a projection operator, but not exactly. It doesn't square to itself, but squares to 1 over n times itself. Okay, that's not very difficult to see, given that rho old is written as this kind of thing, identity times some projection operator, u dagger. So if you square it, u dagger will cancel, then externally u dagger will sit. This squares to itself with 1 over n squared. Okay, so so you can see that it is almost like an operator of that kind.
So
okay.
This one rho old nm of late.
Yes, late. Yeah.
So you introduced earlier H black hole as sum over all the HMs, right? HM2.
Yeah, yeah.
Now what you are doing? I mean, you have only one Hilbert space, right? Which is just
That's
direct
right.
sum over.
But within that, there are subspaces, and these operators relate them. Okay. Fine. So let's get back to our old black hole now. So rho old now at late time can be written as u rho old at time t equals 0 u dagger. Okay. And rho old itself was 1 over n times the identity matrix tensored with 0b 0. Okay. So you can check, this is not difficult to see, that you can show that rho old nm is basically equal to 1 over n times cn star, or maybe since it's an operator, I should put dagger. Okay. So it is just being computed in the radiation state n and m, and you can show that that is a value. Okay. Fine. So one thing that one can easily see here, which we couldn't see in the earlier description, is that rho old late squared is equal to 1 over n times rho old late. So it's almost like a projection operator, but not exactly. It doesn't square to itself, but squares to 1 over n times itself. Okay, that's not very difficult to see, given that rho old is written as this kind of thing, identity times some projection operator, u dagger. So if you square it, u dagger will cancel, then externally u dagger will sit. This squares to itself with 1 over n squared. Okay, so so you can see that it is almost like an operator of that kind.
So
okay.
This one rho old nm of late.
Yes, late. Yeah. Yeah. It is at time t equal to tau. Okay. So now let's try to find out the mutual information for this system. Okay. So you get Sn or system A is equal to log of n minus beta E bar, which is emitted one quantum. Okay. S late radiation is log of Z plus beta E bar. Okay. And the mutual this thing, which is Sn or A RL, this quantity is equal to log of n. Okay. Fine. Okay. So you can find what is the mutual information between this, and this number turns out to be just log Z. Okay. One could try to do the similar computation for young black hole, and that number is little larger than this. Okay. It turns out to be 2 times log Z plus some beta E kind of factor. Okay. So one may ask a question as to why this number has changed. It is not quite clear as to whether this number mutual information should have really gone down this way. Okay, so this is one of the suggestions that they have is that you write down an explicit Hilbert space corresponding to late radiation and write down the density matrix corresponding to that, where you integrate out early radiation. Then things are a little better, okay? That at least you have mutual information which doesn't vanish. So which seems to indicate that the black hole horizon may be smooth in this particular case, because it is not going to contradict with the information that at horizon you have entanglement. You do seem to have something there, even for the old black hole. Okay. So let me change the track and ask what is error correction. Okay. So let's start with classical error correction, and then we'll go to quantum error correction. So we basically have information in terms of 0 and 1, okay, and we want to ask how do we kind of ensure that the data stored is correctly, is correct and there is no error in that. So let's do since we are doing the classical thing, let's do make 3 copies of this data, just to make sure that we kind of keep track of it. Okay. So let's write down a state like this. Okay. So this 0 would go to that, and 1 would go to 1, 1, 1. Okay. It can be done with any number actually, but 3 is at least first non-trivial one. Okay. Any other number also can be done. Okay. So suppose, so in this particular case, you can happily detect what is the value and put it back. There is no problem because it's a classical problem. Okay. So fine. So suppose you don't have this. This is what you should have, and you are trying to kind of make multiple copies to ensure that you keep the data correct. But suppose you have this. Okay. So your first entry is wrong. Okay. So this is what is called a flip. Yeah. Yeah. Mutation, or also called a flip.
You're starting with 1 qubit,
yeah,
and it was 0, and you want to try and distinguish 0
you have
from
either
1?
a 0 or 1.
Or a 1.
So you want to kind of store that data, and it should be recoverable at any time.
Yes.
Okay. So what you do is you keep multiple copies of it.
Right.
So in case some data goes wrong, some other data
You
would
can
be
look
good
at 2 others and correct.
Yeah. So you want to make sure that you get correct information.
Right.
Okay.
Okay.
So now let's check what happens. Suppose you have this. Okay. Then you do a check on this, and you find that in the first case, 2 of them say 0, and the third one says 1. So you say that by majority vote, the answer is 0. Okay. So you get correct answer by what is called majority vote. Classical, yes. Okay. But what if 2 of them were wrong? Okay. So then there is a confusion, because if 2 of them were wrong, you would be in some state like this, and it is not clear which one is correct and which one is wrong.
Why are you writing 2 sets of 3 qubits each? You're interested in one per
Sorry?
Okay, bits or qubits.
Yeah.
Shouldn't you be right? I don't understand the notation, sorry. You're
Yeah.
writing 2 sets of 3 bits or qubits.
Yeah, so I have some bits stored, which could be 0 or 1.
Okay.
Okay.
So that's 1 qubit or bit,
One
and then
bit.
you put in redundancy to get a string of 3, right?
Yes.
Are you keeping track of 2 possibilities here? Just
2
to
possibilities here, yeah.
Okay.
So actual answer is only one of the 2.
Right. So it could be 1, 1, 0, and then you're in trouble because it
Yeah.
should have been the
Yeah,
same.
whether 1, 1, 0 is 1 by majority vote, or whether it is 0 by double flip.
Right. But
Okay.
if you went by majority vote, it's unambiguous. You'd say 1, 1, 0 is 1.
Yeah. So you will have, but it's a wrong answer then.
But the
yeah.
probability of 2 things having gone, that's
Yeah,
the kind of
yeah.
thing you do. Right?
So therefore, if you assign a probability p for a flip, okay, then for double flip, the probability turns out to be 3 times p squared into 1 minus p for the third one to not flip. Okay, but then there could be all 3 flipping, which could give you 1, 1, 1 here, for example, and that is the probability of pq. Okay, so the total probability of majority vote going wrong, okay, is 3p squared into 1 minus p plus p cube, which is 3p squared minus 2p cube. Okay, if this quantity is smaller than half, okay, then you would say that majority vote is still going to be fine. Okay, Now it may seem kind of smaller than half, it seems like a very weak condition. But what one could do is that instead of taking 3 bits, you can take n bits. Okay. So replace the number of copies by n, and in that case you get the formula which is like probability of majority vote going wrong, which is probability of error, goes roughly like e to the minus n times epsilon square, where probability of making a flip is say half plus epsilon. Epsilon could have any sign. Okay. So for large n, it seems like a very sharp Gaussian. Okay. And this Gaussian is quite sharp provided epsilon is reasonable value. Okay. But if epsilon is exactly 0, then you are in trouble. Then you have a completely random setup. Okay. So this is the kind of stuff that you would do if you are doing classical error correction. Okay. But let's try to ask a question: what happens if you do quantum error correction? Okay. So quantum error correction, first of all, has multiple problems, something the classical error correction didn't have. So let's first list the kind of errors that it can have. Okay. So the first is the, or rather 0th level error is the same error that the classical one has, which is the bit flip error. Okay. So it's something like this happens. Okay. Second one, which is what I call 1 really, is phase error. Okay, so bit flip is basically state 0 goes to 1 or vice versa. Okay. Phase error means if you have a state 0, it goes to 0, but a state 1 goes to -1. Okay. Now that is a bit serious thing, because if you have, because you are doing looking at quantum system, you write down a state which is a function of some continuous variables. Okay, and so you could write down a state psi, which is a times 0 plus, or let's take very specific number, it doesn't matter, but b times 1. Okay, if you do that, and if there is a bit flip, then this goes to a0 minus b1. It's quite a different state. Okay, so that kind of error which also can happen. Then the third thing that can happen is what is called small error. Namely, you could have a state which is, okay, let me say that something like you have a times 0 plus b times 1, okay, and that goes to something like a plus epsilon times 0 plus b times 1, okay. It could be b minus epsilon also, but like anything of that kind, okay, there is a small change in that parameter, okay. Fourth problem is no measurement. Okay, that means if you disturb the system, then of course you cannot store the data. Okay, and the fifth thing is no cloning. Okay, so you cannot even clone the data, unlike what you did in the classical system. Okay, so how do we do error correction in a quantum system? So,
no cloning because that would violate linear simplification.
Yes, yeah. Okay. So, suppose we want to store a data 0. Okay. So, for that we define a state, let's call it 0 bar, which is like this. Okay. And for state 1, we define a state 1 bar, which is, okay. So same example, now we are looking at it as a quantum system. Okay. Now these are qubits, yeah. So the data stored, so one thing I also want you to notice is that the data stored, or what is called the code subspace in the Hilbert space, is much smaller than the actual Hilbert space that you are writing down. Okay. So to ensure that you don't make error, you have larger space, but the coded space is smaller. Okay, something which is going to be important. Only 2.
And
yeah.
there it was, you had, I don't know what the classical thing would be, but it is not exponential in the number you're coding for, is it? I mean,
Yeah, there also.
It is 3. I guess you're coding for 1 with 3, but here you're coding for 2 with 2, 2
yeah,
with 3.
that is
so
right.
it's an exponential.
Yeah. Okay. So what is the meaning of this? By this I mean that like if you want to write down a state A0 plus B1, okay, you replace that by A0 bar plus B1 bar, okay, which is okay. So now let's look at what are the things that could go wrong with this, because we have to find out the error without making any measurement. Okay. So let's define a state by x, y, z. Okay, whatever is that reading. Okay, and we know that like we are looking for something like 0, 0, 0 and 1, 1, 1, and we are going to make a distinction between that. Okay, so define two observables. One observable is y plus z, and the other observable is x plus z. Okay, and this plus is basically y plus z mod 2. Okay, so this that is a notation that you add the numbers and write that mod 2.
So Dileep, you think you can wrap up in another 5 minutes or something?
Sorry?
You think you can wrap up in another 5 minutes or something?
Yeah, I will do only the quantum error correction. Actually, I won't be able to do anything of its application to. Yes, yes, yes. So I'll do this, but I'll have to show the connection. So I don't know, but let me at least do that much and stop. Discussion. Okay. Yeah, but that's okay. At least half an hour I could do something. I can do something for half an hour at least. Okay, let's. Yeah, that's right. Yeah. Okay, let's see. Okay, so let's take our state to be x, y, z, to be 0, 0, 0. Okay, and then you operate these two fellows on this, and you get an answer 0, 0 for both of them. Okay, and you would say that therefore there is no error. Okay, if you act it on 1, 1 also, you will find that there is no error because it is defined mod 2. Okay, but now you notice that instead of the state 0, 0, 0, suppose you have a state 1, 0, 0. Okay, now if you do that, and now you operate a state like these two operators on this particular state, then your answer would be yz, which is these two, will give you 0, but xz will give you 1. Okay, you could do this for this state as well as this state, and the answer is 1, 0 and 1, 1. Okay, and notice something interesting about this, that 0, 0 is a correct state, there is no error. So if this test returns zeros to you, the state is correct. If this state returns any of these fellows, then not only it says that the state is wrong, but it tells you where the state is wrong. Because in the binary numbering system, this is 1, this is 2, and this is 3, and that is precisely the place where the number is flipped. Okay, so quantum error correction not only tells you that there is an error, but it also tells you at what place there is an error, so that without doing a measurement of that qubit, you know that you need to flip that qubit. Okay?
So what if we do the linear superposition, because that's something that could happen?
Yes.
There are 8 states here.
Yes. So suppose there is a small error, for example. So then you could have a state which is like this, which goes to right. So in this case also, you can, of course, you would have 1, 1, 1 with minus epsilon. Kind of stuff. Okay. Then take a state like this and do the following thing. You ask, so you do this test on it, and you ask what is the probability that you will get answer 0, 0. Okay. And the probability that you will get answer 0, 0 is 1 minus mod epsilon square. Okay. Then there is a probability that at mod epsilon square when the answer is 0, 1. Okay, because the first fellow is flipped. Okay, so whenever it gives 0, 1 as an answer, you take your qubit and flip the first guy. Okay, so even if you have a linear combination, probabilistically it tells you exactly which fellow to be flipped. Okay.
So the answer is 0, 1, you flip the first guy.
0, 1 is binary number is 1. Right, 0, 1 is 1, So one tells you that the first bit has actually flipped. That is why with this probability the error comes. So anytime you get this kind of answer, then you say that like you are going to flip the first bit and then only you store or utilize it. Okay.
Sorry, I don't know the rules of the game, but you can do it so that you don't turn 0, 0, 0 plus epsilon 1, 0, 0 to 1, 0, 0 plus. I mean, you flip that.
No, because you have, because the answer comes out to be 0, 1, right? So 0, 1 in binary is 1. So it tells you first location has an error.
I understand, but and then you can do an operation so that only you have a linear combination.
Yeah.
Only one term in the linear combination.
That is right, because when you did that experiment, it came with that. I mean, of course, it is statistical answer. You do it several times, and when you get this answer with less probability, next, yeah.
It's not probabilistic, it's actually completely deterministic prescription. What you do is not uncertainty, but you actually do conditional operations.
Okay.
So the conditional operations involve measurements, which is what you write x plus y.
Yes, I'm doing a measurement on not
depending on the result of measurement, you make the corresponding flip.
I see. Okay.
Yeah, but I still have to do.
You get something only if it were 1, 0, 0,
Yeah.
and then you flip that.
And anyway, until now, it is all the classical code. Okay, he has just written in a quantum notation.
Yeah.
But the quantum mechanics hasn't just come in yet.
Yeah, but like nevertheless, this determination is not done by a single test, right? That you get a wrong answer with probability epsilon square is not done with a single test.
Not a single test.
Yeah.
Conditional operation.
Yeah, but they correspond to doing multiple tests on it. Yeah, yeah. So in that sense, it is a probabilistic this thing. But then you know exactly what is to be done with the state. Okay. There is no probabilistic nature after that. Once you have figured out that this is a erroneous bit. No, you do a multiple tests on it, not answerable.
Multiple tests. You don't want to have many, you just have 3 qubits.
Yes.
But you do multiple tests.
Yeah, yeah.
In that sense, it's not like this is an answer to an ensemble question.
No.
It will not be a
No. So no single bit is being tested, but you are doing multi-bit testing at. Okay. Is that okay? So should I continue? I'll continue.
I don't know exactly, but perhaps in the discussion, a very short summarizing might be a good idea, because the discussion is already loaded.
Yeah.
Okay,
so I think I'll stop here. But like main point that one wants to utilize here is to say that occurrence of error is basically interpreted as Hawking radiation. Okay, that and you want to ask a question that whether you can correct the black hole data, okay, such that you could show that there is a unitary evolution. That is the main point that one wants to get at.
What is the correction of radiation?
So the idea is basically that whatever I have written out here, you basically treat a black hole as a quantum device which has stored data. And the information is leaking out of that quantum device, which you call Hawking radiation. Okay? So that whenever information is leaking out, you basically would get a error. So you define an operator which will do an error correction for you. Okay, and so that you could still continue to have unitary evolution. Okay, so the purpose is to write down an error correcting operator and show that error correcting operator along with this unitary time evolution operator gives you a total unitary evolution of the entire system. That is the idea.
How does it address amps?
No, in fact it doesn't address amp. They show that like after doing all this they get a firewall in fact. Yeah, yeah. They show that in certain special cases you get a smooth horizon, but typically you would get a firewall. Now, at least in the first paper, this is what they are trying to say. So main point is that like you attach an auxiliary Hilbert space to this entire system, then you have a black hole system entangled with the radiation. You get it disentangled by this auxiliary space. Radiation is entangled with the auxiliary space. You transfer the entanglement to that, purify the black hole. Okay, but then at the end you have to get rid of this auxiliary space. And when you get rid of this auxiliary space, or whatever they call ancillary space, okay, then you have to dump that entropy back, the entanglement back into the black hole. And that actually generically keeps growing the black hole entropy. Okay, so only way they can say that it would make sense is if there is some drama happens at the horizon. Okay, but they have one situation in which they can show that there is a smooth horizon, but that is not a generic case. So maybe let's pause here. Yeah, sure. So I'll stop here.